Yeah. So first, I would like to use this opportunity to thank the real organizers, Mukun, Douglas, and Monica, for taking care of everything. I'm sorry I didn't do any organizer's work. And so today, yeah, I'm planning to discuss the operator growth, means how simple operator becomes complicated, and I'm sorry that I don't think I'm too knowledgeable about other literature. So I think I would start by talking about our recent work Alex Stracher and I, and that's based on the generalization of the previous work of Douglas and Dan and Alex. And then, but feel free to interrupt me anytime, and I will be very brief on introducing our results. And there will be some new things I want to mention. That's my ongoing work. And I would like to emphasize that this work is really almost all Alex's work, and a lot of the things I feel very excited about. Actually, I only understood after I read the draft he wrote. So, ask him if you have further questions. Okay, so I will start from general things. So I want to emphasize that now, before I mention SYK, there's a lot of interesting general structure of operator growth that applies to all fermion systems. So, let's consider Majorana fermion system. So you have these Majorana fermions, and we know it has a Hilbert space of dimension of 2 to the n over 2, right? So it's like n over 2 complex fermions. And then in that Majorana fermion system, the size of operator is simply, so let's say this is a fermionic operator. Then the superposition, then you can expand it in some superposition of these, and so on. So you have something like that kind of expansion, and then so it's just like viewing this as a wave function. So you can think of these operators as eigenstates of numbers. So a size. So size 1 and this size is 3, so on. So that means the size is actually an operator on the space of operators, which means that you take any operator and map it to a number. Right? So this is like a linear operator defined on the space of these operators, which is a space of dimension like d squared. So it's convenient to map that to a more familiar Hilbert space of states. That's what we call a trick of doubling. So let's say you have an operator like psi. We can map it to a state. So I draw this picture. It means an operator that acts on the Hilbert space of these Majorana fermions, and gives you another. It acts on one state, gives you another. But we could introduce a doubling by introducing a state living in 2 copies of the system. And this thing here is a particular state which I call I. And that particular state is your choice, but you want to make it maximally entangled between left and right. And that's important to make sure you don't lose any information. You preserve the trace, the inner product between operators. So in this Majorana fermion systems, there is a very simple choice of I, which makes the calculation much easier. Which is now this is a system with 2 copies of these Majorana fermions. So I have psi I left and psi I right. And then, so now I define a complex fermion operator, which is something like this. So in my notation, if psi squared is 1, then I need a 1/2. So you can define a complex fermion operator, and then you define I to be the ground state, which means the number of fermion for each little I is 0. And that you can check is a maximally entangled state between the 2 copies. So once you make that definition, then the number operator has a very simple form, because the psi I left now the mapping I defined, which maps operator to state, is for each operator, you map it to a state by acting this operator to the left. So an identity operator is mapped to the state I, and the other operators maps to the operator x on I. So because psi I left is simply f plus f dagger, so you see whenever you apply psi to the vacuum, you just create a fermion. You apply another one, you create another fermion. So this n is actually just the fermion operator, fermion number operator. So the size operator in the doubled Hilbert space is simply fermion number, which you can also write as something like that. Okay, so that's very convenient because because this is quadratic, so we could study many properties of it. And okay, so just by using so once you do this mapping and look at the notation, look at this general formula, there is already some surprising, for me it's kind of surprising consequence. So let's look at the size of a particular operator, which is take thermal density matrix. Say this is thermal density matrix, and let's take rho beta 1/2. So the reason why we consider that operator is when you apply that to the maximally entangled state, this is simply the thermal field double at that temperature. So it's natural to use that state and to represent a system with finite temperature, and that's the main goal of our work, that we try to generalize the previous results to finite temperature. So the first thing we can check is what is the size of this operator. So if I draw this picture, then your familiar picture of thermal field double, like a semicircle, right? So that means I'm applying this half of the thermal imaginary time evolution to get that state. And then when I calculate the size, the average size, then basically I'm taking that state and calculate the expectation value of the size. But that's basically the semicircle, and then with this fermion bilinear in the middle. So you see that, sorry, there is a sum over I. You see that this expression tells me up to a constant, this is just 2-point function with fermions. So this is just thermal circle for the fermion 2-point function. So after you carefully check the sign and so on, it actually looks like it's very simple. It's simply determined by the fermion 2-point function.
Sorry, so do we know the form of the Hamiltonian, or is something?
No, we didn't say anything about the form of the Hamiltonian. So this is general. Of course, the Green function knows about the Hamiltonian.
Okay, just assume there's a Hamiltonian which does that.
Well, no, for any Hamiltonian, I'm just writing down the thermal field double state.
Oh, okay.
And then calculate the size of that. So the size operator definition is independent from any Hamiltonian. So for any Hamiltonian, you can calculate what's the size of rho 1/2 at a given temperature.
Okay.
And the answer is that's determined by fermion 2-point function. But more precise, it's like average over flavors fermion 2-point function. So this already tells you a lot, because it tells you, for example, first of all, when beta goes to 0, there's no beta dependence of the 2-point function, so g is 1. And this goes to 0. That's what should happen, because rho goes to identity. That's what happens when temperature goes very high. But when beta goes to infinity, you see that we know most systems have g beta over 2 goes to 0. For example, if you have only one ground state and there is a gap, then you are trying to excite something from the ground state, and all the coordinate function decays exponentially in imaginary time, so it should go to 0. If it's a CFT, we know the form of the 2-point function. It also goes to 0 at beta. It also decays with beta at this value, right? So you have a 2-point function like this, and this value goes down when you go lower temperature. So for almost all the systems we know, except maybe you have like a degenerate two ground states, and the fermion operator can take you from one to the other. Except these very special cases, this goes to 0, and that means rho beta half has a size. So I use this to represent that. Rho beta 1 half has a size that goes to n over 2, which is like the size of a random operator. So you have the size of operator can go all the way from 0 to n over 2 and then to n. But a random operator will sit in the middle. A random permutation operator. So this tells me like almost all the systems, when you take a 0 temperature limit, the density operator actually is as big as the random operator. I would thought it's big, but I didn't expect it's as big as a random one. Okay.
And that goes down as you
increase temperature.
The temperature to the point where it becomes 0.
Right. It becomes 0 when at the infinite temperature, because there is no beta dependence. This is just a UV 2-point function, which is 1. And another surprise is the same quantity shows up in the size of another operator. So let's consider I start from the thermal state, and I apply an extra perturbation to it. I apply an extra perturbation. Let's say just to be concrete, we say I equals to 1, fix one of them, and at some real time t. So the reason why we consider this is obviously we want to make connection to out of time order correlation function, and this is like how when in the bulk picture you shoot in some particle and look at its overlap with some final states. Okay, so this in terms of the picture is just I have the thermal field double, and then let's say this is left, and then I apply some operator here.
Sorry, actually,
yeah?
I mean, very naive question. So is the definition of n basis independent?
N?
Yeah.
Sorry, which one? This one?
Yeah, right.
It's independent from the single particle basis change, but
sure. But if I do I can just call like 3 fermion times together as a fermion, and then I call a single fermion.
That's certainly not basis independent. I mean, I don't think there is any basis independent way to do that. Yeah, you have to first. I don't think there is any way to specify size of operator that's basis independent. Because if you look at the SUD, then everything is the same. Right? I mean, yeah.
That's fine.
So all these operators squares equals to 1 or minus 1.
Exactly.
So I think they can all be transformed to each other.
Yeah, right.
So all the notations about simple versus complicated operators needs to first define a Hilbert space tensor factorization.
Okay. But the statement that the rho to the power 1/2 has the length n over 2 is that do you think that's a general statement, or that's a basis dependent statement?
I think if you change, as far as I can see, this is. So I think if you go to a different basis, it will be determined by some other 2-1 functions. So, but I'm not sure. I think if you make that 2-1 function of some extremely complicated operator, this statement may not be true. But probably for most choice, that's still true. Like you may be able to fine-tune that operator so that the 2-1 function doesn't decay. I don't know if that's possible. Or if there's a gap, I think for any basis this should be true.
I mean, extending that, might you say that maybe there's some natural basis that's sort of preferred by long-term dynamics, as sort of all the operators grow and saturate, and there's some sort of preferred representation of that, and with respect to that,
I don't know. This is a general. I think this is an interesting general question that we should discuss. So it feels like the notation of what operators are considered as simple is kind of determined by the observer, determined by what we think are simple. I mean, the only thing that should be general is what you call simple operator is a small set. Right? It's some small part of that exponentially many operators. But other than that, it seems like this is really, there's no absolute reason why certain operator works better than others. It's really about whether there is an algebraic small set of operators that could generate other. Yeah, it's like generate the other operator by taking products of them. That maybe that's a requirement. Like we want a small set of operators that when you take product between them, they generate the whole algebra. And then there is a notation that about complexity of the operators. Like these are the simplest, and then how many of them is considered as a measure of the size. That's the most general thing I could imagine.
Is there a sense that if we require the Hamiltonian to be local, then that writing it in a local way will sort of fix the basis?
Yes, that's so. I mean that the other it's when you say the Hamiltonian is local, you have already chosen the basis.
Yeah, that's what I mean.
Yeah.
And
so, but in that case, so this is like some discussion that applies. I mean, I think the whole thing will be interesting only if your Hamiltonian is like K local. Like the Hamiltonian is not arbitrarily complicated. Hamiltonian contains it's like S like K contains some small number of terms. But if in addition it has spatial locality, then you have different possible notions of size. You could talk about spatial size or size in terms of just like that counting. Like if you have spatial locality, then you could have an operator here which evolves into that tone, and it could have something like, say, it occupies this side, not this side, and this side, and that side. Then in this notation, I would call it has size 3. But you can also measure just the spatial size. You say it's that. So there are different notations there, but I think the most general one, which doesn't refer to spatial locality, is this one here, which I'm just counting how many sides it has an attribute support on. Although this is like a boson, like a qubit version. I may mention that later, but this is like, I mean, you could do the fermionic one or the cubic one, the bosonic one, and they are not they cannot be mapped to each other easily, because if you do Jordan-Wigner transformations, these simple fermion operators become complicated in bosons. So another example that you need to make a choice.
I mean, you might be taking it too far from where you want to go, but suppose you have a 2D conformal field, what would you characterize as a useful basis? Just the primaries or the primaries and descendants?
That's an interesting question. I think there are different choices you can make. Say if I imagine a lattice model that gives me the CFT and long wavelength limit, then I can do different choices. Say if this is a fermion model, I could do this definition so that even on the same site, I could have simpler operators and more complicated operators. Or I could also just use I could also say I only care whether the operator occupies that site or not. Like any operator on the same site, whether it contains one fermion or 3 fermions, I call that size 1. And I can only count the spatial occupation. I think this depends on the. I don't see there is a preferred choice. And also, like if you look at say OTOC and CFT, and your OTOC, I'm going to show that your OTOC is only done with these fermions. Then that will prefer one choice, which is this choice.
Yeah, because then you could, for example, in the example you described, you could even ask a refinement of what I asked, which is suppose that's the Ising, and you got it from some fermionic system. But I wanted to talk about the dual free boson picture. Then bases are not mutually local with respect to each other. So
yeah. So jumping ahead a little bit, I think what happened is put let's say let's say I'm talking about the size of this operator. Then if I do something like the psi I 0, psi 1 LP, rho 1 half psi I 0, psi 1 half, it's 1 over I. If I do this OTOC, that's measuring the size in this notion. But if you want to measure size in other notion, you could replace that psi I by a family of operators, say, for example, the primaries in the Ising model. Then it will be a different measure of size. I think the common feature of all these measures is these operators are all local. So in terms of measuring where the operator is, they do the same, but they give different weight for different operators. Yeah, so in general, you could do something like that, yeah, I think. Okay, so go back to this. Sorry, go back to this. This is what I want to draw there. So the reason why this measures the size. So what does this quantity, this out of time order correlation, what does that measure? It measures the size difference between that state and this state. So you could show that this is equals to the size of psi rho 1/2 minus the size of 1/2 itself. And basically, in terms of diagrams, it's like the semicircle represents the thermal field double, and then there is a operator that goes to real time here. And I'm calculating the size of the operator, which itself is the bilinear fermions. And then so you take the inner product with itself. Right, so there is a psi t. So you see this is like the out of time order correlation function. And then you need to subtract a constant part, which is done by permuting these two orders. Yeah. So more generally, you could replace this by any other operator here. But if you are using this definition of size, the other pair of operators is always single fermions. Oh, so the interesting generic feature is what happens if you go back to t goes to 0. So let me call this delta n. I will call this delta n of psi 1t rho 1/2. And this is a quantity that we are going to study a lot. So the interesting thing is even if you take t go to 0, this is not 1. I mean, even if you don't have the rho 1/2 thing, then you are just comparing zero size and 1 size. Right? So the difference will be 1. But on the background of that rho 1/2, you are asking, this quantity is saying, if I add an additional fermion to that already existing fermion thermal gas, what's the size change? And interestingly, the answer is not 1, but something kind of renormalized. And so you just take, let me take delta n t goes to 0, and then let's just put this back to t equals 0, and then the anti-commutator is simply some delta functions, right? So sorry, is this? Okay, so the anti-commutator becomes a delta function, and therefore you get a 2-point function from that because 2 of them canceled, and then you actually get back the same 2-point function. And this is some quantity between 0 and 1. So again, if you take beta goes to 0, this is like infinite temperature, and you get 1. If beta goes to infinity, then like your operator is already maximal sized. You apply another thing, it's still, I mean, your operator size distribution is like here, and you do something, it's still here. So really, it tells you that quantity determines not only the size of the thermal operator itself, also determines when you add an additional fermion, how much does that size change. This is so Alex gave this a name, delta beta, and it's called the fractional scrambling distance. So the reason why we call that name is this formula. So it's like so my rho 1/2 is somewhere here, and I'm drawing it as a distribution because it's not an eigenvector of the size operator. Right? So it's some distribution here, and that value was n/2 times 1 minus delta beta. So that means this distance is like delta beta times n/2. and every time you add a new fermion, it moves by delta beta. So it's like the whole scale shrinks by that factor. Sorry, there was a, yeah.
Well, I mean, I see the two ends, and I see that it should be monotonically going between 0 and 1, but is there a, I mean, this seems almost like defining the G, which already had its own meaning, so is there some other reason to expect that there is an underlying connection apart from it going from 0 to 1?
Well, this was the. I mean, no. The point is that from the physical thing, it doesn't seem there is a reason they should be the same quantity.
Right.
And it seems. I mean, I can only say mathematically the reason why they're the same quantity is some algebraic reason. Like when you take anti-commutator, it's a number. So it's not. It depends on some details of the algebra. But physically, yes. But the physical picture is basically.
What you just said?
It's basically you already have. So this rho 1/2 is like a. So schematically you can draw it like this. Like diagrammatically, it's like some operator that contains a lot of fermions, and then now you add another one to it. You add another one to it. Then there is a chance of collision. So there is a chance that you actually shrink the size by 1 rather than increase the size. And so this equation, this two, the relation of the two is basically saying it is the size of rho 1/2. You don't need to know any other detail, just the average size of rho 1/2 that determines the probability of collision. I think that's basically what it's saying.
But this is predicated on adapting the growth to the single fermion basis, right?
You mean it relies on that? It relies on that definition. I think it relies on. I mean, it certainly. Everything was like when we averaged over the more precisely, if you don't average, if you really take psi 1, then you may get the two-point function of that psi 1. So it's only equal to that after we average over flavors. Yeah.
Is it easy to see that you actually need the anti-commutator to get the size in that formula?
I think that's because we subtract. If you don't, so this first one is the out-of-time order coordinate function. Yeah, I think what I wrote here was there was some problem because all the three things should be on the left and one on the right.
Well, my question is if we don't write anti-commutators, but instead write the usual OTFC, A, B, C, D, something like that, and don't subtract the second piece. It's not obvious that you actually need the anti-commutator. They differ by some phase factor.
Yeah. So let's be more careful. Yeah. So I think it's not. I mean, I think that this difference involves the anti-commutator, but let's be more careful here. So the first term is this picture, which is after I go back to the single copied language, it's psi 1 t psi I 0 psi 1 t, and then there is this semicircle. So the other one was psi I of maybe I put I here, beta over 2. So this is not a trace. This is thermal equilibrium value. And then the second term was the two-point function, just psi I.
Okay.
And so I think you could write this difference in terms of anti-commutator here. So I think what I wrote earlier was not the right expression because I have 3 operators on the left and 1 operator on the right. So if I write this, it's sorry, it's a little chaotic. Everything. Okay. It's a discussion about chaos. So like psi 1 IT psi I 0, there may be a minus sign somewhere because I expect what showed up is anti-commutator rather than commutator. But it's something like this. Psi IT psi I. Sorry. One of them is 1. Psi 1 I 1. beta over 2. Yeah, so it's kind of...
Oh, this term. The second operators are without anti-commutator.
Right.
Okay,
I think this looks more correct. Yeah.
Yeah, because there is an important difference between the double commutator and NO2C like that.
Mm-hmm.
There is a factor like cosine kappa
pi over 2. Yeah. Yeah, I think this is the one that's this is the one that contains the leading. I think there's another one which has the subleading term, right?
Yeah. So
vanishes
this
in maximum
is with the SYK model at low temperature. This O2C is large, and the commutator or TSC is of the other one. It doesn't contain beta J.
Mm-hmm. Yeah, so I think so part of this consequence of this formalism is to make a choice between the different regularizations. And well, of course, we could also put this point here and look at the size of that operator. Yeah. So, but if you look at the operator that starts from similar to a double and apply an operator in real time, then that's what we get here. Okay, so in summary, the general thing we learn is some picture like what I was trying to draw here. So let me draw it again. So it's like at infinite temperature, the picture is there is n over 2, which is the size of the random operator. So, and then when you start from a simple fermion operator which has size 1, then if you do time evolution, the size is going to grow, and in the end it goes here. So it starts from here, and then so maybe I start with a very sharp peak, and then it moves this way. So that's the general picture. And when you have finite temperature, then the picture is like, I also have the n over 2 here, but I start from somewhere here. But sort of the grid here is also smaller. And the number of spacing here, the number of points here is the same n over 2. So it's like you rescale the whole thing. Because every time you add it, so you start from some operator that was already here, and you add a fermion to it, it moves a little bit by that unit, delta beta. So that's kind of suggesting that the whole picture is renormalized with the delta beta is like a renormalized size of a fermion. So I will just very briefly mention what happens to SYK. The calculation involves some more details. But so the key interesting thing is because this, sorry, I just erased it, because the fermion, the number operator itself is only a bilinear fermion. So we could not only just study n, like the criterion value of some size, we could also consider higher moments. We could put all these into a generating function by defining something like this, and then later by defining like that. And let's call this the mu of the psi. And you just you could expand this in mu and then get all the different moments of the operator, so of the size. So you not only know the average size, but you know the moments. And that's very nice because n is bilinear. So in the case of SYK, we could put this operator in, and we can still do the G sigma action and solve it. I can't. Alex did. If we only had the solution analytically, we only have the solution in large Q. Yeah. So basically the picture is, so this is originally the SYK model, and now let's start from just the 1/2 case, which is that semicircle. So if you calculate this thing, Without the insertion, it's like partition function, thermal partition function. With the insertion, because the insertion is bilinear, so basically what happened is the fermion comes here and then goes out, crossing this boundary, goes out at the superposition of things here and there. But this whole thing is just a symplectic transformation of the fermion. So it's like the same problem, the Liouville problem Douglas discussed yesterday, but with a twist boundary condition. Instead of the antiperiodic boundary condition of the fermions, you have a twist boundary condition, and so it will imply some boundary condition for the two-point functions. So in terms of the two-point functions, so this domain we draw yesterday, a domain with the boundary condition here. That was this Liouville problem Douglas mentioned yesterday. So now you have a twist boundary and these lines. So you still have that periodicity, and then you have this boundary condition here, and in addition you have the twist boundary conditions along these lines. Like the two-point function cross that boundary and it becomes the superposition of things here and here. Anyway, so once you find the saddle point solution of the two-point functions, you could determine these generating. You could determine the generating function, and basically, so this is like the partition function of this twist boundary problem. So let's call that C mu rho 1/2, and then in addition, if you put a fermion there, and we are going to do another continuation to put it in real time. So let's say if you take first derivative of mu as mu equals 0, then you get the size of this operator, and here you get the size of that operator. So the difference is actually determined by the ratio of the two. And but the ratio of the two is actually just the two-point function with that background. But this is like the partition function with the twist, and this is in addition you have two insertions. So what happened is the two-point function is this, and then when you do an expansion of that, you get the distribution of. So the expansion of this is not directly a distribution of the size of any operator. It is actually describing how the distribution changes from here to here. That seems to be the natural generalization of the size distribution of psi 1 of psi t at the infinite temperature. So what I mean is, if you take this equation and expand in mu, or more precisely expand in e to the I mu, then you get so basically this operator is expanded in a sum over things with different size. Schematically, it's like if I view this as a state, the sum over size of different values, and there is a probability for each size. Right? So there is a size, and then there is a probability. Right? So there is a probability for size n for that operator, and there is also a probability for that. And so the expansion of this actually is telling me how you convolve the probability distribution for the thermal operator with something else. And that's like a probability that describes how the operator is changed by psi of t. So basically you start from some distribution like this, and then you add a little bit to it, this thing changes a little bit. So this k was like the moment expansion of g, and that's like a deconvolution of this formula. Yeah.
So if you start with something that's larger than n over 2, does it allow you to?
I think there's a symmetry between the two sides, because the product of all fermions is a conserved number. Is fermion parity. So you could take anything shorter than n over 2, just multiply this, it goes the other side. So it's always symmetric. So we should think of this as like a potential with a reflection wall in the middle. That's also special to that definition. If you define like qubits, then like Polyvol operator at size 1, identity at size 0, then the random operator will have size 3/4. Yeah, so basically the point is that you can get the whole distribution, and then I'm just going to write down, one formula for the SYK case, which is how the average size looks. So the size change that we wrote there is just given by the first derivative of the 2-point function, and what we get is in large Q you get something like that, where this is growing exponentially, and alpha is that alpha is I think half of the Lyapunov exponent. So as a function of temperature, it starts from like pi over beta, and it becomes the UV value J in high temperature.
Delta beta is 1 at large Q?
Delta beta in large Q is 1.
So why did you write that expression?
Yeah, that's a good question. So if we just do the large Q expansion to the order 1 over Q, we cannot know whether it's this or that. But we need to include this factor to make two calculations consistent with each other, because if you take t go to 0, this is delta beta, and we have the general UV calculation which knows that's delta beta. So this is actually I think it would be nice if we could do a higher power in Q calculation and verify that's true. But so far we only have the argument that to be consistent with UV, and also when you go back to low temperature limit to be consistent with things known in low temperature, we need to put in that factor of delta beta. And just the large Q expansion to the leading order doesn't tell me whether it should be this or that.
It doesn't tell you whether delta beta is multiplying the second term, for example.
You're saying that the earlier argument gave you a delta beta shift to begin with, but it's not clear the correction term, which will be exponentially going to be delta beta.
Yeah. Yeah, I agree. It doesn't prove. Yeah, we don't have a proof that.
Delta beta depends on.
Delta beta is in large Q limit is order. It's like 1 minus order 1 over Q. More precisely, it has the form of like alpha over J to the power 2 over Q. So when Q is very large, this is close to 1.
So alpha is 1 or half of the Lyapunov expression.
Yeah.
Alpha is half of.
So alpha over J is always between 0 and 1. Yeah.
Okay.
Yeah. If I plot alpha over J, this will be 1 here. Yeah. So yeah. So I think.
Another question?
Yeah, I think that's true. Yeah.
You could also define this by taking delta n for like rho to the 1/4, psi 1 of t, rho to the 1/4, or
Yeah.
some other. Is there something nice about this one?
I think this is the one that, if I understand correctly, I don't have a very good understanding on this. If I understand correctly, this is the one that compares well with the ADS wave function also.
Can you say a bit about what the ADS wave function is?
Yeah, so that's what. So So that's related to, I think, what Lenny talked about last week. So basically, if you think about this bulk picture, and then you put in some particle, so this is like shooting in a particle from some earlier time. And by the way, shooting a particle here corresponds to this rather than putting it in the middle of thermal circle, right? I mean, you're applying a Fermi operator on one side, and then the claim is this particle goes into the bulk, and if you pull out how its momentum depends, I think the momentum means quantum number of this generator of the SL2R. Then momentum as a function of time, it looks like that. So there was the proposal that the size there's a comparison between the size and momentum. But moreover, I think the claim is even the whole wave function here, which I mean the first moment, even the whole wave function there agrees with how this particle is going to propagate into the bulk. So the particle is going to propagate into the bulk. We know the bulk boundary correlator, propagator. Then you can plot its momentum distribution, and it also agrees with that. So I think that's one of the open questions that I want to mention. It would be nice to make the whole analog more precise, the mapping to the relation between this and the bulk boundary propagator. And so far, I mean, it's an analog in terms of the format. In the large Q limit, I don't know how general that is.
So when you say you can get the distribution of the momenta in the bulk, what exactly? I mean, that's a single wave function which is trailing?
Yeah, but then you could plot that wave function in momentum basis rather than the coordinate. So it has a probability distribution.
But a single particle.
It's a single particle, yeah. So here I have a wave function leaving somewhere. Then you could write the momentum space wave function. As you could write 1 over n a n. This is like the eigen function. So then a square is like that.
A calculation that I remember working, I don't know if it's exactly the same as what you're describing here, is you could take the single particle eigenstates of the generator that's global ADS time translation.
Yeah.
So it's not momentum, it's like global energy. And there's a discrete set of those eigenfunctions. And you can expand the state where you acted with psi1 of t in those single particle eigenfunctions. And that, I believe, is this wave function. At least it was a rescaled version of the infinite temperature wave function, which I think is the same as what you find here.
So let me try to understand this in higher dimensions. Because in higher dimensions, there's a basis of discrete states for the conformal algebra, which are just the eigenfunctions in global ADS.
We probably want to be using a black hole. Maybe we could do it in Rindler space, but in order for this size to be growing rapidly, we want to be doing one of those things.
This is all just
I was going to imagine dropping a particle into Poincare ADS or Rindler and expanding it into the global wave function. That's a problem, but the analog is problem.
With respect to Rindler time.
With respect to Rindler time, I see.
Right.
You could ask about the global energy of the particle, global ADS energy.
I see. And you're saying if you look at the coefficients and plot them, they will agree with this moment distribution function.
They at least agreed with a rescaled version of the infinite temperature one.
Right. And this wave
function is.
Yeah, it's the same format as the So this analog with the ADS wave function was already pointed out by Douglas and Dan and Alex's paper. But in that case, it was the infinite temperature. Here, the point is that in large Q limit, it's the format of the whole distribution is the same, except that rescaling. Other than the rescaling, there is an important thing, which is renormalize the coupling constant. So the infinite temperature case, just take alpha equal to j, then there is this change kt squared. So you could view like when you go to find the temperature, this goes to that, and you could think of that as a renormalization of the coupling constant j. So basically, what happened is it's like effectively you have a j effective, which is changing in time. In UV, when very short time, it is the j, because when t goes to 0, this form and this form are the same. but within the time of the Lyapunov time, or it renormalized to alpha.
Is this statement the same as saying that if you go from global wave functions to regular wave functions, and if you look at the appropriate Bogoliubov coefficients, they have this exponential growth, and it's this exponential growth they're identifying because of the coefficients that have exactly with these inches and coshers. Is that the feature that you're seeing, or or am I misinterpreting this?
This isn't exactly a Rindler wave function, because the Rindler wave function would be something with infinite global energy. This is like a wave packet.
It's not a Rindler wave function. It's
a particular time on the boundary.
Good, but if I'm looking at the creation and annihilation operator in the Rindler basis, they would have the appropriate Bogoliubov transform. So if you make a wave packet with those creation and annihilation operators, and then we try to go back to the global basis.
Normally that's a function of frequencies. Here we're discussing time, Rindler time, and global frequency. That's a different kind of change of basis.
It seems that these relations work so well at large Q because there is only one functional dependence. Everything is related to the infinite temperature by some kind of rescaling.
Right. So yeah, so that may be the reason. So schematically, it's like the previous calculation of Douglas et al. Was like a diagrammatic calculation, and here the result was suggesting that we just dress every line, and the diagrammatic structure was the same as before. I mean, like we dressed every line by a different like renormalization of the coupling, but somehow we don't need to worry about these more complicated diagrams. Yeah, which I think this is probably the consequence of a large Q.
Yeah.
So in general, yeah, we don't expect just a rescaling of the infinite temperature.
Yeah, it's not a question of whether we want to include more diagrams, but how do we normalize those diagrams? Because you're using time as a variable.
Mm-hmm.
You know, a more natural variable may be something like momentum, as you say, and it may be the null energy actually on one of the horizons.
Mm-hmm. You mean using that as a variable, then the finite temperature and infinite temperature look the same?
No. Suppose the finite temperature looks different. Then there will be differences between different measures of caps.
Mm-hmm.
And to me, it seems that a more natural measure would be using this null momentum instead of n, the number of particles.
Why null momentum is the right thing to use?
The null momentum.
It's the thing that appears in the out-of-time order correlator, for example, in the bulk calculation of the out-of-time order correlator. So if you express the boundary wave functions in terms of that basis, then it's easy to calculate the out-of-time order correlator.
So do we expect, so from a boundary point of view, is that's something that's different from the size operator, or do we expect them to be proportional in some limits?
I'm not sure.
Isn't there a general relation in your setup here between this distribution for size and the out-of-time order correlator?
It's only the first moment that's out-of-time order correlators. The higher moments will be because if you have higher powers of n, then you could view that as an out-of-time order correlation function with more complicated operators. Yeah, it's like psi of t, psi I, psi j, psi k, maybe something like that. Psi t, psi I, psi j, psi k, beta over 2. Yeah. Trace expectation value. I think this kind of thing will show up when you look at higher moments. Yeah, it still involves only 4 points in time.
Xiaolang, can I try to understand the motivation? You know, I'm more used to the original paper. If I calculate the out-of-time correlation function, I have 2 parts. One part is this h equal to 2 non-conformal part, plus a lot of high energy mode with conformal part. So here, can I say this diagram also has two parts?
The large Q expansion is a different way to decompose the 4-point functions. So it basically only has this one term, but that one term, if you expand it in the h equal to 2 and the higher h, I think it includes all of them.
So this includes all of them?
Yeah, so it's not just h equal to 2.
This 1 over Q expansion also has...
Because
the higher mode will modify the Lyapunov exponent?
Yeah. So the large Q expansion applies to any temperature, right? So the Lyapunov doesn't have to be maximal. It could be any, it could be anything.
At low temperature, it's still maximal.
At low temperature, at low temperature, go back to maximal, and in that case, you will. I think in general, this large Q expansion contains all these different H, but when you go back to low temperature, the contribution of other things will go down, and you only have H equal to 2. That's my understanding.
Okay.
I heard there is a holiday party, so maybe I don't want to go over time. Unless now you want to go, but maybe the last thing I want to mention, I won't have time to go to the other things. But I want to mention a little bit of the epidemic model, what we mean. So I think there is a nice, there's an interesting intuition here about this renormalization stuff. That like in the infinite temperature picture is basically like spread of a disease. You start with 1 and then you pass the virus to a few people and then continue. So it's like I have a bunch of people here and then it grows exponentially, but then it will saturate when enough people got sick. So then, but then the finite temperature case is, so the thing that this kind of model doesn't capture is the fact that there is a conserved quantity, which is energy, and so when you have the conserved quantity, it means there is a particular operator which doesn't grow. It's conserved, is always the same. So that's what also if you use a random circuit kind of model you cannot capture that. So when you have this conserved quantity, it's like some of the people are already immune to this flu. So then they don't grow, and you cannot spread the disease to them, and they also don't contribute. This population was frozen. So the whole thing was like just a slower growth, removing that population. It's kind of like two populations versus, in the infinite temperature case, it's like two populations, the contaminated and not. And then in the finite temperature, it's like three populations, the immune and the sick and healthy.
Is the disease deadly?
I mean, I don't know. In the end, everyone got it, and then.
I mean, the guy dies quickly enough, he may not be able to give it away.
And what I mean is, like, instead of this, you do that. In the end, you all go to the same state.
You're still missing the flip symmetry.
Sorry?
Even in this, you're missing the flip symmetry.
Right. Yeah. So I mean, we should probably just restrict it to n over 2. Like all the higher operators, you just view them as. Actually,
but then it's not smooth. I mean, you can't just flip it by hand, right? You really want to build in the.
No, it's like n over 2 is already the maximum you can get, and then you're right. Yeah, so like when I'm at n over 2, I could reduce the number and increase, and it's the same effect. Yeah, you're right. That doesn't count. That doesn't capture that part.
So it's like a small subset limit of the actual model.
I mean, if you make this more precise, you could capture that, because like in the random circuit model, like if you have a SYK but the J is random in time, then you could, in the large n limit, you could really write down a differential equation, classical differential equation for n, which is like something like this, and there's a gradient flow, and V is something like n squared minus n to the q with some coefficients. Sorry. It's symmetric, so it's like n minus 1/2 minus, if I remember correctly, it's something like this. So basically, it's a potential like this. shape. This is in the middle. Sorry, this n is like so yeah. So you start here and you grow exponentially because you are flowing down with a gradient flow, and there is a downward potential, and then it slows down and goes here. So yeah. So I mean, this is basically like a epidemic model. It tells you that if you have some number of people already sick, then the spread rate is proportional to that. But there is another term which tells you it slows down when you have some number of people that's already contaminated, and you cannot spread anymore to them. Yeah. So apparently there are many open questions in relation to the bulk and relation to physical observables. That's what I'm working on now, which is about how if you study some physical observables, which is like 1-point function and 2-point function, but you study that with different initial conditions, and then you look at how strongly your response property depends on the initial condition. That could tell us about the size growth and the auto time of the correlation function. And there are other open questions I was hoping to mention. I think a big open question is how do we make this kind of intuition more precise? Basically, when you don't have conserved quantity, everything can be described pretty well by a random circuit kind of model. Like just forget about the coherence between different time. But once you want to understand the effect of conserved quantity, which I think the main effect is just reduce the Hilbert space size, but we don't know how to make that more precise. And of course, all these discussions can be generalized to higher dimensions, where there will be interesting questions like, how do I see when I reduce the Hilbert space size because of finite temperature, I reduce the butterfly velocity? Like these kind of questions can all be studied. But the problem is we don't really have a effective model like that which could describe this.
So does your V function, does it apply to all Q? As you've written, there's a 1/Q.
This one?
Yeah.
Yeah, this applies to all Q as long as you have larger n. In general n, this is not a number, so I cannot view this as a classical differential equation.
For large N.
Yeah. So for large capital N, the n little n is a mean field, can be described by a mean field, and it becomes just a gradient flow. I'm done. I'm open to. We can continue the discussion if you don't have to leave now.
Could you say more about the observables? What are the observables and what are the small perturbations?
Okay, thanks for giving me the chance to say that. I've just listed the results. So that's something I'm working on now. So there are two results I want to make statements. The first one was very simple. If you take any operator, then you take expectation value in a state. And let's say this state is random. It's totally random in Hilbert space. Which means the measure is like R, or you could say psi is U times the reference, and U is the R random unitary. If you do that and you look at what's the variation of this, like how much does the expectation value depend on the state? So look at that, and this line means average over states. This is simple. You can work it out and something like this. And I could write that as this infinite temperature expectation value of O square. This is assuming O is traceless. So this is 0. Okay. So that has a simple consequence. This mathematical result has a simple consequence, which is if I look at O as a commutator of two operators, then this is the response. So say I prepare my system in a given initial state, and then I'm looking at the response of some perturbation. So this is the response coefficient, or in general T and T prime, theta T minus T prime. So this is the retarded one function. And then now I ask how strongly does that depend on the initial state? And then you calculate this, you see the fluctuation is 1 over d plus 1, and then the commutator square at infinite temperature. So basically what happened is I numerically check some of that, and of course it works. But basically, like schematically, it's like if you start from different states and look at the response as a function of time, then it does something like that. But then when you look at how big is the fluctuation, it does something like this. That profile was the auto-time order coordinate function. So in principle, this is a way to measure OTOC for a system that's not too big, because this factor, the d is the Hilbert space dimension. So it's something exponentially small. So you probably cannot see it in many items. But if you have like 10 qubits or 12 or 20 qubits, it's still possible. And then there is a related but different observation. Because like preparing a random state is difficult in experiment. I guess, I mean, it's difficult to make sure it's like really random and highly entangled. So the second thing I want to consider is closer to experiments, which is you prepare an initial state that's product of random states. Like just put all the spins into random directions, right, for qubits. That's easy. That's a different ensemble. And it turns out that if you study similar quantities in that ensemble, I can already see something about operator growth even by one-point function rather than this kind of two-point function. So let's consider some operator and then measuring that operator at time t with the initial state psi, this initial state psi. And now I look at the same quantity. I look at how does the fluctuation depends, how does the, when I vary the different initial states, how big is that fluctuation? And there is a simple expression, which is something like OT squared. This is just a normalization factor times. I'm going to explain what this means. T plus 1. Sorry. So what this means is, I don't know what's the best way to erase. What this PR means is you look at OT. The PR is basically the probability distribution we talked about of the size. So I'm now imagining a qubit system. So this O of T is a superposition of many operators, and then so if you look at its wave function norm square, it has a probability PR occupying that region R. Say this is the region R, for example. Then I can ask what's the probability that the operator is exactly supported on this region. That's PR. And this is the weighted superposition of the different regions, the different size of the operators, weighted by some exponential factor. And the little d is the dimension of every site. So if your operator has a sharp peak distribution, like your operator is mainly just occupying a particular R with a small fluctuation, then this is approximately just something like that, like exponential of the size of the operator. In general, it may have a big fluctuation.
So is that average the average over all site X?
Which average?
I mean, that
yeah, this is averaging over the random states on every site.
Every site.
Yeah. So like you independently choose all of the.
Right. So we have to prepare a lot of states.
Yeah. It's always actually. You may not need too many states, because how many states you need to prepare, it depends on how the higher moments are suppressed. So basically, like there is a distribution. Like when so say calculate this quantity for different psi, and then it's something like this for different initial states, and then it seems like even, I mean, numerically when I try this with a small number of random states like 100, you already see a pretty good estimation of the distribution. I think how good that is depends on the force moment, whether the force moment is big.
Okay.
Like if you have a Gaussian distribution like this,
Sure.
then you just randomly sample a field, you already know the width. It's really, the higher moments are not very large, then you're fine. And I think the higher moments are surprised by other factors, the 1 over d probably. So numerically, I think that's not the difficulty. The difficulty is the whole thing itself is very small. I mean, that's less a problem here. In that approach, the whole thing was surprised by 1 over d. So it's not like you need to sample many initial states, but the problem is for each initial state you need to measure it many times, because otherwise, I mean, the response property itself has noise, right? It has fluctuation. You do one measurement, you don't get the expectation value, but you get like one of the eigenvalues, and then you average over them. That's the real problem. But here it's slightly better, because I think what shows up in the vector is like 1 over the dimension of Hilbert space of the region R rather than the whole system. So at the initial time it's a little better. But
can I ask about those regions R? It's the sum over all regions effectively where you have support of the operator, and regions of any size that the operator has support of.
So basically, when you expand the operator, you get, let's say I have a poly or 3 polys and so on, or 2 polys, and then so each of them has a support in some region R. So I take all the terms with the same support, and then look at sum over their coefficients. Yeah, so it's like I have a wave function for polys on site I1, on site I2, on site I3. Let's say this is the region R, which is given by these 3 labels. And then there's 3 polys on each of them. And you just take this and sum over all the alphas. And that gives me PR. But so you need to be careful you avoid double counting. This doesn't include the operators that actually are supported on a smaller region than R, a subset of R. I excluded that, just exactly R. And so numerically you could see like this noise will go down because the size go up. Numerically you see the fluctuation of this quantity goes down like that, which corresponds to the size grows and saturates. Yeah.
For the result corresponding of the observables, if I want to apply these to, for example, SPK model, is there a way I can see these results from the G sigma action or from a certain?
I mean, this proof doesn't depend on anything. So for any
right, I was trying to see if I can reproduce the result from a certain model, like without using these operator groups.
I don't think you can calculate that in G sigma, because you need to choose a random initial state, and all the G sigma calculation will be in equilibrium. But yeah, so in SPK basically you can directly calculate this side and the other side. But maybe there's some meaningful question, like what if I replace this random state by some other ensemble, like maybe thermal double state with a very long time evolution, average over time. You could ask, yeah, you could. I mean, presumably that's random enough, so maybe similar things happen. But I think you need to change the way to ask that question.
Maybe calculated by this double scaling method yesterday. Double scaling this chord diagram. Can we calculate this quantity?
Well, I guess the point is that this equation is simply true for all cases. So we could calculate the OTOC in different cases, like different double scaling or different. Yeah, but that's all about the right side. This is just saying if you experimentally measure this, prepare the random state. In principle, there is a way to measure the OTOC and measure the exponential growth if you have exponential growth. I mean, this is a very simple result, but I kind of like it because it's like has the same flavor as the classical Lyapunov. Classical Lyapunov exponent is defined in terms of the sensitivity of the initial condition. So you change the initial condition, something deviates exponentially. So here it's similar to that. Except, I mean, you prepare different initial states and look at how strong that gives you a deviation of your response probabilities.
This was suppressed by
yes.
the number of Hilbert space.
It's 1 over Hilbert space dimension, so it's that's the that makes it very.
Quantum effect, does it have classical counterpart? Classical counterpart, the real perfect point has no such suppression.
That's an interesting question.
Classically, maybe this one is better because this one has small t, right?
This one is better at the initial time, before it spread to the whole system. But I'm confused. Yeah, I'm confused about why. In that case, what happened in the classical limit? There must be something in the. I think there must be some definition in the operator v and w. Like if you take some classical limit and your v and w are classical variables, maybe there's definition which cancels the 1 over d. But I'm not sure. That's an interesting question.
Any other questions or comments?
Thank you.